we're going to do, as an example, both positive and negative ions for phosphorus. Now, before we can do the ions, we need to first do the atom. Okay? So I'll do the orbital notation and electron configuration for the atom of phosphorus first. Phosphorus is on the third row of the periodic table. So that means that we have to have a completely full first period, or first primary energy level, and second primary energy level. Since phosphorus is on the third row, the third period of the periodic table, then that means that represents the filling of electrons in the third primary energy level of the phosphorus atom. Phosphorus is in the P sublevel region, so we have to fill up the S sublevel region in the third primary energy level first, and then get to the P sublevel. So the first primary energy level. Now, to do the orbital notation and electron configuration, you have to have the element symbol followed by a colon. That's required. If you don't have those in there, that's 2 points off on the problem. So that's an easy one. Make sure you put that on there, okay? So we're going to completely fill up the first level. The first level, 1, the first primary energy level, 1, only has an S sublevel. So the placement of hydrogen and helium, we're doing the region of the periodic table, and you were asking about that a minute ago. When we do the region of the periodic table, these first two columns over here represent the S sublevel. And helium really belongs right here, okay, because it's part of the S sublevel. So hydrogen and helium, hydrogen will have one electron and helium will have the second. And those two arrows represent spins. They have opposite spins because you want to cancel the electromagnetic repulsion to get two electrons in the same orbital. Okay? So once we've filled up 1 and the first level only has that S sublevel, we're ready to go to 2. Lithium and beryllium are in the S sublevel region, so we need 2s, and we need 2 electrons for lithium and beryllium. Then we get to boron over here. We're going to completely fill the P sublevel region over here. Boron, carbon, nitrogen, oxygen, fluorine, neon. So that's 2, and the P sublevel region has 3 orbitals. 1, 2, 3 orbitals. Yes, you'll have the test references. Okay? So you can use any of the test references you want. And so far, you've only really needed 2, at least in this unit. And that's the main periodic table and the one that has the oxidation numbers on it. Okay, and we're going to use both of those right now. Okay? So you're going to put, since we're going to completely fill that, we're going to put 1 electron in each of the boxes, and then we're going to go back and pair them up till we get all we need. Well, we need all 6 here, so we're going to completely fill those. You got a question about this?
Can we write that diagonal thing on the test reference?
I'm not going to put it on the test references. If you want to, the first thing when you get the test tomorrow is to make out that diagonal thing you're talking about, which is the mapping. Well, I had a copy of it here somewhere. Oh, I've got it up there. Okay. There it is up on the board. You can, I mean, it's really easy to do, and it might be, if it's helpful to you, draw it out somewhere. But don't draw it on my test references. Okay? I'll give you some scratch paper or something if you want it. All right? And please don't throw things in class, okay? All right. So we have 3s, then that's the next thing we get to after 2p. So we filled up 2p and we're going to 3s. Okay, that's right here. We're trying to get the phosphorus, which is in the third row. Well, first we've got to fill up 3s before we get to 3p over here. So 3s only has 1 orbital, 2 electrons, and then we can get to 3p where phosphorus is located in the P sublevel region. P sublevels have 3 orbitals, and phosphorus has 3 more electrons in that third primary energy level, P sublevel. So 1, 2, 3. Remember, 1 in each box, and then pair it up if you need to. We don't need to pair anything up this time. So you don't have a pair of electrons in the first box and 1 in the second to get to 3. It's 1 in each box. Okay? So that's the orbital notation for phosphorus. Now let's do the electron configuration. Oh, that's not electron configuration. Phosphorus. 1s, and what we do is simply count the electrons in the S sublevel. You have a question? The periodic table?
Yeah. That S right there?
Right here?
Yeah, if we was doing that, wouldn't you put like one more electron?
You would. You have one more right here.
Okay, I was just thinking.
Okay? So we just count the electrons in the sublevel. 1s, 2 electrons, 1s, 2. It has to be a coefficient 1. It has to be a lowercase s, not a capital S, so it's got to be half the size of the 1. And it has to be a superscript 2. Okay? And then this is 2s2, 2p6, 3s2, and then 3p3. And that's the complete electron configuration. This is orbital notation up here. And this is both for the atom. Now then, we can write a shorthand version of the phosphorus if we wanted to, which we call the noble gas electron configuration. And for that, we find the next lowest noble gas. You might have to. We covered it in this unit. You might have to. So phosphorus is element number 15. You just count your way back. 15, 14, 13, 12, 11. When you get to a noble gas, and all the elements in this last column over here are noble gases, and so that's our next lowest noble gas. And what we're going to do is replace that part of the electron configuration that matches up with that noble gas configuration and replace it with a symbol for neon. So neon's electron configuration is all of this right here. Say 1s2, 2s2, 2p6. So what we're going to do is we're going to replace all of this right here with the symbol for neon in a bracket. It has to be in a bracket. And we can just finish out the remainder of the electron configuration. Okay, so that's the noble gas, the electron configuration. For the atom phosphorus. Okay? Alright, now, we're ready to start getting the positive and negative ions. Let's figure out what the positive and negative ions are by looking at the periodic table with oxidation numbers. Okay, so here's our periodic table with oxidation numbers. Now I have a 5 plus version, a 3 plus version, and a 3 negative version. I want to do the first one and the last one. Okay? The 5 plus and the 3 negative. You with me? Well, we haven't really gotten into the theory that gives us this 3 plus. Okay? No, it's whatever I give you. In this case, I'm giving you 5 plus and 3 negative. Okay? I won't give you one we haven't covered the theory for. All right? It's not that much more than what we've learned, but we just haven't learned it in here. Okay? All right. So what I want to do is to write out the orbital notation for phosphorus in pencil so that I can erase stuff if I need to. Okay? Let's do the 5 plus first. So the symbol for the 5 plus is phosphorus 5 plus. Okay? And it's called phosphorus 5 actually. That's the actual name of it we're doing. Okay? Phosphorus 5. So that 5 Roman numeral doesn't mean that it's an atomic mass of 5. It means that's the charge on the phosphorus. Okay? Now I haven't taught you that. It won't be on the test, but I'm just letting you know what the name of it is. Because we talked about what the negative ion would be. We haven't talked about positive ions yet. We will talk about that in the next unit, I think. So 5 plus. So what we want to do is to write out the orbital notation in pencil. What? I will when I get there, when I do that, yes. When I remove electrons to get there, I'll put that 5 plus on there. But I'm glad you know what's coming ahead. It means you kind of get a grasp of what's going on here. That's great. So here's the atom. All right, there's the orbital notation for the atom. Okay. Now, to get a 5+ charge, I have to remove 5 electrons. So phosphorus, going back to our other periodic table, has 15 protons, and the atom also has 15 electrons. So 15 protons are positive, and 15 electrons are negative. So they're balancing each other out so that the actual atom is neutral. So this is a neutrally charged atom. To get a 5+ charge, I've got to have 5 more protons than electrons. But I can't change the number of protons because that changing the protons would change the atom. All we can change is the electrons. So the way we do that is, to get a 5+ charge, we've got to get rid of 5 electrons. So what we want for a 5+ is to remove 5 electrons. Does that make sense? So we have 15 protons and 10 electrons. So we're going to remove all these electrons in the highest energy level. So now that I've removed 5 electrons, Michaela was right, I also have to have a 5+ charge on here or it's not correct.
Okay, do I have to write out all of those boxes in the last?
No, technically all you really need is this. That's a 2, even though I kind of messed it up. So really, once you remove all those electrons, those orbitals don't really exist anymore. You don't have to draw them out. No, not for this. If you mean by erasing, no. I'm just showing how to get there. If you fail to write these out and then erase, a lot of students get it wrong. So I would do it this way, even though you may not need to. It's a way to make sure you got the right answer. Okay, what's your question? Exactly, it is basically neon. And that, well, well, we could do that. Yeah, I'll get to that, okay? So here's the thing. The point is that all elements want to have 8 electrons in the valence level, right? Isn't that the octet rule? So we're reviewing the octet rule now. All elements like to have 8 electrons in the valence level, except for the really small ones that want only 2. They want to have a valence level that's like a noble gas. A noble gas has 8 electrons in the valence level. So that would get phosphorus down to a valence level, what remains anyway. It's not really phosphorus' valence level anymore because we got rid of that. But what remains has a full valence. That makes sense? So you're absolutely right. You nailed it. Okay? All right, so the electron configuration then, we have to have that 5+, and it's 1s2, 2s2, and 2p6. All right? And if we did the shorthand version, since we got rid of all this, to get to this orbital notation, the noble gas configuration for 5+, I'm sorry, it should be a, I know, I'm having all kinds of trouble today, is just this. Okay? So that's the question you ask about using. All right? Any questions about that? All right, that's 5+. So this is the orbital notation. This is the electron configuration. This is the shorthand or noble gas electron configuration. Let's do 3 negative now. Now this you have to know. You have to know. Yes, I'll get to that too. Quiet, please. All right, so 3 negative. Which one we're trying to get to? What's the name of a 3 negative ion? How do you change the name to IDE? So this is not phosphorus 3, it's just phosphide. Now this one you do have to know. We have covered that in this class, that negative ions, negative monoatomic ions, only the monoatomic ones, the ones that are single atom size, will have an ID ending. Well, usually it's the last syllable, but phosphorus just sounds funny when you say phosphoride. Phosphide just sounds better. Like oxygen, you take out both the last two syllables. You know, if you had a syllable in there that really doesn't belong in there, I'm not going to count off about it this time, right now. We're just kind of used to it, okay? Oxygen, phosphorus, sulfur, they kind of do some funny things. Everything else is one syllable. Okay, yep.
So there's 2 letters you don't do the I.
2 letters you don't do the I.
Like if it's
No. Monoatomic. Oh, if it has 2 atoms, not 2 letters, but 2 atoms, 2 elemental symbols. We haven't gotten to that yet. It'll be a couple of units before we get to that. Okay? But I'm just trying to make it clear now that the ID ending only belongs on monoatomic ions. Okay? Alright. So for this then, let's do the orbital notation again for the whole atom. So that's the atom's orbital notation. We want to have a 3 negative charge. Remember that protons are positive and electrons are negative. What do I need to do to the electron structure of phosphorus to get a 3 negative charge? Add 3 electrons. 1, 2, 3. And I can't forget now, I've got to then put a 3 negative over here for it to be complete. Okay? So that's the orbital notation for a phosphide ion. Its electron configuration then is 1s2. Remember, lowercase s, superscript 2. This has to be a full-size coefficient number. 2s2, 2p6, 3s2, and 3p, what is it? 6. Okay? And then a 3 negative over here. Okay? Alright, Micah. You were sharp about figuring out what the orbital notation of this is. What is this orbital notation electron configuration? What's it the same as? Same? No. I've got a full 3rd level now. That has a full 2nd level. So what element does this? Well, will this have the same electron configuration as? Argon. Very good. Guys, that's important to know. It now has a full valence level. Its electron structure is like that of argon. What now? Pretty much. That's the point behind the Octet Rule, why it works. Okay? So let's talk about now, real quickly, about the shorthand or noble gas electron configuration. Since we added electrons on here, we can't shorthand all of this as argon. We can only shorthand the part that's the neon part. Okay? Because it's based off what the original atom was. Okay? Alright, so then the noble gas electron configuration takes out just the neon part and leaves the 3s2 and 3p6 on the end. Okay? So that covers all of that stuff, I think, pretty much, the ion stuff, by doing one like that. Okay? Any other questions about that? Oh, the dots. Yeah, good point. All right, let's go back up here real quick and let's look at the dots. This is the electron dot formula then. Let's review that. Let's look at phosphorus. All you have to do is count the number of electrons in the valence level. And remember, the valence level is the highest primary energy level of the atom. So how many electrons in the highest primary energy level of phosphorus? 5. S and P are part of the valence level because what we're really looking at is this coefficient number. Both of these are 3s. That's the highest level, highest primary energy level. So it's 1, 2, 3, 4, 5. So phosphorus, the atom, is going to have 1, 2, 3, 4. Remember, you put 1 dot on each of the 4 sides, and then once you get 1 dot on each of the 4 sides, you pair up on any of the 4 sides you want to. I'm going to choose to do it down on the bottom, okay? So that's the electron dot formula for a phosphorus atom. Then the phosphorus 5, or phosphorus 5 plus, we have to remove all 5 electrons. Okay? So that electron dot formula will have no electron dots on it. But we have to have a 5 plus charge written on it. So that is, while that's also the symbol for phosphorus 5, it is also the electron dot formula for phosphorus 5, because we removed all the electron dots to get that 5 plus. That make sense? Now, the phosphate ion, we have to have the phosphorus atom, but we added extra electrons to it. So we started out with the 5, but we added 3 more electrons to get that 3 negative charge. 1, 2, 3, and then we put a bracket around it to show that 3 negative charge. So that's a phosphate ion in electron dot notation. Does that make sense? You don't understand how I got that? Yeah, we took all. So here's the atom. To get a 5 plus charge, we have to take all 5 of those dots away, right? Because that represents these 5 electrons we took out. Remember? So if we take all these electrons we took out of these boxes are the same electrons represented by these dots. So if we take all those dots away, well, that's what we have left. Okay? You just have to remember where it's coming from to understand what we're doing. If you do it the way that I teach you, which is to write it down, then erase what you need to erase, you probably get it right. What now? We had to add electrons to it. So to show that, we have to put those electrons around it. And going back to Micah's question before, the argon, the electron dot notation for argon is the same, only there's no charge on it. Now neon's electron dot notation would have all those dots around it, because it does have, we're not removing any electrons from neon. So those will be different, but argon will be the same.